Hello, I'm Jay Howden. Today, I'm presenting my work, Semi-Supervised Spam Detection. This work is done by myself under the guidance of Professor Noriko. We are today living in the digital world, where we see an explosion in the use of short messages. Those messages are convenient and can often convey lots of information. However, there also exists lots of spam messages that are usually not expected by the people, and it may cause major harm to individuals as well as society. As shown in the examples, those messages usually do not appear in standard forms, and thus making them hard to detect. Given this, the goal of this project is to propose a technique to detect those spam messages. Generally, spam detection is a very hard topic for researchers, given two reasons. Firstly, most spams only account for a small percentage of total population. The right image illustrates this unbalance of the data we use. In these figures, number 1 stands for the spam. This makes the traditional classification algorithm perform poorly usually. Secondly, spams are often expensive to label given the complexity and varieties of spams. Given those challenges, we need to come up with a semi-supervised approach that firstly do not rely on lots of labels from the dataset. Also, we need some visualization that help the users to label them. Of course, before that, we need to convert the data into some embeddings so we can feed into our model. In this project, we choose bird embeddings. The dataset used in our project is the spam classification dataset from Kaggle. This data has 5,574 total messages, with 13.4% being spam and the rest being normal cases. The data already contains the bird embeddings extracted by the publisher. The bird embeddings has total 766 features, and the values are between minus 0.63 and 0.32, as shown in the image. Now we're going to talk about some of the key parameters used in our model. So the algorithm used in our project is called ADOA, and it was first published in 2018 for anomaly detections. The basic idea of this algorithm is that since we only have few labels, the algorithm needs to use some assumption to auto-label other cases. This assumption is that anomalies are often isolated from the rest of the population, but similar to other anomalies in distinct clusters. Given an unlabeled point, the isolation score is computed using a state-of-the-art anomaly detection algorithm called isolation forest. It measures how isolated the point is to the majority of the points. And the similarity score to each cluster is computed using the Euclidean distance between a point to the cluster of an anomaly cluster formed by the labeled anomalies. Those two scores measure how likely a point is an anomaly in our case. Of course, it is spam. Then after we get the isolation and similarity scores, we then take the weighted average of those two scores. This weight is called the theta, and it is one of the hyperparameters. The higher this scores, the more likely a point is a spam. Also, there are two other hyperparameters. Alpha is a threshold value for spams. If a weighted average is above this level, the point is auto-labeled as spam. Beta is threshold for normal case. If the weighted average is below this level, then the point is auto-labeled as normal case. Then we can input those auto-label points with a weighted average of isolation and similarity score being the sample weight into a designated classifier. In this way, we can train a model to detect the spams. Since our model requires some initial labels from users, we want to use some interactive visualization to help the users to label the point. The upper figure is the scatter plot generated using principal component analysis. This helps users to label a point. The figure below is the violin point, which shows the distribution of similarity and isolation scores. The number of clusters is set by the users using the button on the top right corner of the scatter plot. When a user places the mouse cursor over a point, a black line will show up on the relevant position in the violin chart to illustrate its isolation and similarity scores. To evaluate the performance of our algorithm, we compare it against the isolation forest, which is one of the mostly used unsupervised anomaly detection algorithm. The hyperparameters are tuned using a 5-fold cross-validation, and the train test split is 70 and 30. The plot illustrates the result. The x-axis is the number of labels given by the users, and the y-axis is the AUC score. As you see, our approach is significantly better than the baseline approach. Although our approach works well in simulations, we need to do an error analysis to find out the reason for errors. In my findings, I categorized into 3 varieties. For each reason, I listed both false negative and positive cases. The first one is the message contains some irregular and unrecognizable symbols. Those things are often not in standard forms and have vague meanings. The second one is when messages being too short. Those messages are often categorized in wrong class. I think the reason for that is that they do not carry enough information for the classifier to detect properly. The last one is a sentence contains some abbreviations and the phrases. Those phrases often do not appear in standard English and will sometimes confuse the classifier. That's it for my presentation. Thanks for watching.